Forget all about crocodiles and sharks, because 400 million years ago, the most fearsome river predator was a creature of a completely different kind. That was Jaekelopterus, a gigantic arthropod, a sea scorpion that actually lived in rivers and estuaries. With an estimated length of up to 2.6 meters, 8.5 feet, Jaekelopterus wasn't just a giant, it was the pinnacle of evolution in its environment. So how did an animal with a tough shell and massive claws become the dominant hunter? What set Jaekelopterus apart from any other animal in its rivers were its outsized chelicerae, the enlarged front claws. A fossil claw found in the Klurf Formation of Germany measures 36.4 centimeters long, but the tip is missing. With the full length restored, the complete chelicera would have reached about 45.5 centimeters, nearly half a meter. By comparing that ratio to other giant members of its family, researchers estimated the body length between 2.3 and 2.6 meters, or roughly 7.5 to 8.5 feet. Not all scientists agree, however. Some studies suggest the claw-to-body scaling may exaggerate the true size, pointing instead to a maximum closer to 1.8 meters. Others maintain the larger estimates are accurate. Either way, the chelicerae were extraordinary, and their function tells us far more than their size. Unlike simple grasping limbs, these appendages were heavy curved weapons built for force. You can imagine an enlarged version of a lobster's claw, but far more robust, slamming shut, with enough power to puncture armoured fish plates or crack through tough exoskeletons. The detail visible under fossil preservation reveals what that power was used for. Along each edge of the claw ran rows of denticles, small tooth-like projections that varied in size and orientation. They acted much like serrations on a cutting tool, ensuring slippery or thrashing prey could not pull free once trapped. In young individuals, the denticles were comparatively thin and fine. As the animal grew, adults developed much larger, thicker denticles, some dramatically elongated for piercing and holding. That shift in claw structure suggests their diet also expanded with age, from smaller arthropods and soft prey to strongly built armoured fish. Evidence of those encounters has even been found in the fossil record. Puncture marks on the head shield of a Devonian fish called Lecreaspis patula, discovered in Utah, have been linked to Jaekelopterus howelli. The spacing and pattern of the damage match what the large chelicerae would inflict. It is a rare but direct glimpse into how these giant arthropods attacked. Together, the denticle ridges the changes during growth, and the bite marks left behind confirm a predator adapted for grasping, tearing and overpowering prey in rivers that were crowded with armoured organisms. But these claws were not only dangerous to other species, they could just as easily be turned against fellow Jaekelopterus. With weaponry designed to pin and crush cannibalism becomes a realistic possibility, especially in times when rivers shrank or food was scarce. Fragmented fossils and signs of damage on specimens hint at intraspecific clashes, while direct proof is scarce. Both functional anatomy and the ecological pressures of Devonian rivers make cannibalism plausible. In that scenario, the same claws that crowned Jaekelopterus as an apex predator could also make it the greatest threat to its own kind. Altogether, the chelicerae reveal an animal whose dominance relied on specialized hunting tools rather than sheer bulk. They were not general-purpose limbs, but precision weapons evolving as the predator aged to secure an ever wider range of meals, and even to compete with rivals of the same species. Power and gripping strength made them lethal, yet there was another element needed for those claws to strike effectively. Strength alone could not turn a seize into a kill, only precise targeting could. And to understand how Jaekelopterus achieved that accuracy, you have to look at its eyes. Hunting success for Jaekelopterus depended not just on raw power, but on a visual system that stood out among Devonian predators. Its compound eyes were unusually advanced, built from thousands of small lenses working together to form a mosaic image. While many arthropods of the time relied on rudimentary sensitivity to light and motion, Jaekelopterus carried a system optimized for detail. Researchers measured an interommatidial angle of about 0.87 degrees, comparable to that of modern predatory arthropods, along with photoreceptors about 70 micrometers across, extraordinarily large by arthropod standards. This arrangement closely resembled the eyes of modern horseshoe crabs, suggesting adaptations tuned for sharpness even under murky conditions. This wasn't just about detecting movement, it could resolve edges and track prey shapes in dim, turbid water. A narrow interomotidial angle meant finer detail, while oversized photoreceptors collected more light in environments where visibility was limited. Together, these traits balanced acuity with brightness, producing eyes designed for rivers shaded by plants, muddied by current, or darkened under clouded skies. In fact, this combination may have allowed Jaekelopterus to switch between daylight hunting and feeding in gloomier waters with little disadvantage. One of the clearest functional benefits of these eyes was stereoscopic overlap. Although the eyes were placed laterally on the head, their fields of view overlapped just enough to provide depth perception in front of the animal. That overlap mattered. It gave Jaekelopterus the ability to gauge distance, accurately timing strikes so that the chelicerae snapped shut at exactly the right moment. It wasn't human like three-dimensional sight, but it was sufficient to convert raw claw power into efficient attacks. For a predator relying on ambush strikes, even slight improvements in depth awareness could mean the difference between securing a meal and wasting a lunge. The comparisons also show how unusual it was within its broader family. While Jaekelopterus and species like Pterigotus anglicus show this high level of acuity, others such as Acutiramus appear to have less refined vision. That variation suggests the group included a spectrum of ecological strategies, from specialized hunters to more opportunistic feeders, but Jaekelopterus falls firmly at the sharp-sighted end. The details extend to life history as well. Fossils of smaller individuals suggest wider interomotidial angles in juveniles, meaning that their vision was blurrier and depth perception weaker. This probably shaped an age-dependent hunting strategy. Younger Jaekelopterus may have targeted easier or slower prey, relying less on precision and more on availability, while adults refined their eyesight to track fast fish and accurately align their claw strikes. Linking visual development to diet and behavior helps explain how members of the same species could avoid competing directly until the largest individuals rose into the role of apex predator. Photoreceptor dimensions further reinforce this specialization. At about 70 micrometers, these light-sensitive cells were enormous compared to the 1 to 2 micrometers typical in many animals, including humans. The trade-off for increased size is loss of some sharpness, but in dim water, the benefit outweighs the cost. Just as horseshoe crabs today exploit similar cellular structures to perceive contrasts and edges under scattered light, Jaekelopterus likely enjoyed the same advantages along riverbeds. It could identify outlines, track quick shifts in prey movement, and strike while competitors still wrestled with shadows. Taken together, these features transform our picture of Jaekelopterus. It wasn't simply a brute armored with giant claws, it was a specialized hunter that paired gripping power with clear light-sensitive targeting. This made it uniquely suited to rivers and estuaries where conditions change constantly and where precision eyesight delivered a decisive advantage. With its vision and claws working in concert, it could dominate environments many assumed were ruled by more obvious marine predators. And that point raises a deeper question: what kind of habitat could support such an animal in the first place? For centuries of study, the name sea scorpion carried an assumption that these animals prowled in salt water like sharks or lobsters. But the record of Jaekelopterus shows otherwise. Its remains are tied not to deep marine basins, but to river channels and estuaries environments shaped by both fresh and brackish conditions. Jaekelopterus rhenaniae comes from the Klurf Formation of Western Germany, where the deposits preserve freshwater fish and thick mats of plant debris. Jaekelopterus howelli, on the other hand, was unearthed in the Beartooth Butte Formation of Wyoming, an estuarine setting where tides mixed marine waters with river flows. For a long time, we called them sea scorpions. But Jaekelopterus forced a rethink. This giant thrived where salinity never stayed the same. That ability mattered. Rivers and estuaries are habitats in constant flux. Rainfall pushes currents toward fresh water. Tides and storms swing them back towards salt. Animals tied strictly to oceans or restricted to rivers would have found these conditions difficult, yet the very presence of Jaekelopterus fossils among freshwater fish and flora shows an animal that tolerated the full range. Being able to cope with both fresh and brackish waters meant it could outlast marine predators during fresh phases and outlast river specialists during brackish ones. This adaptability helped crown it as the dominant hunter in places with very few other competitors large enough to challenge it. Movement within those environments also left its traces. Hydromechanical studies of pterygotids show that they carried flattened telsons and broad paddle structures well suited for steering and stability rather than sheer speed. With these, Jaekelopterus could hover, make quick turns, or glide forward efficiently, skills ideal for chasing fish in lagoons or along estuaries, but it was not built for high-speed pursuit over long distances. Instead, it was a poised ambush predator, able to use riverside structure and turbidity to its advantage. At the Klurf Formation, the setting paints the picture. Sediments contain freshwater fish alongside early land plant material washed into channels, a clear indicator that this was a system tied more to inland rivers than ocean coasts. To encounter Jaekelopterus here would not mean scanning reefs in clear water, but looking into a darkened river swollen with seasonal floods where detritus and prey collected together. In Wyoming, the Beartooth Butte record adds texture. Their fossils were buried in an estuarine zone where species such as Strobilopterus also appear, showing a community already adapted to mixed salinity habitats. For Jaekelopterus, these areas were perfect frontiers, stable enough to supply food, unstable enough to exclude many rivals. Scaling up these findings gives us a view of a predator uniquely tuned to volatile conditions. Unlike ocean fish, which could depend on steady currents, or smaller river arthropods that clung to narrow niches, Jaekelopterus broadened its range. Fossils scattered across transitional sediments underline that fact. It consistently appears not in the middle of stable seas, but at the edges where rivers met coasts. The supposed sea scorpion was in practice a giant of the rivers and estuaries. The dramatic image often used is to picture one gliding along a Devonian riverbank in place of later reptiles or crocodiles. At more than 2 meters long, it pushed aside shoals of armored fish, took advantage of cloudy waters to mask its strike, and anchored itself in a role few other creatures could fill. This was not a chance. It was the outcome of tolerance locomotion suited to shifting currents and claws, guided by unusually sharp eyes. Yet none of these strengths guaranteed permanence. Adaptability made Jaekelopterus the master of unstable habitats, but mastery itself did not ensure survival. Even powerful hunters can be undone when the balance of a river changes, or when new competitors arrive that exploit weaknesses it cannot overcome. The decline of Jaekelopterus is a reminder that even the most imposing predators can vanish under pressures that build gradually. This section is about its fall, a process still debated without a single agreed-upon cause. Fossil and ecological clues point to several likely pressures, but researchers caution that these are hypotheses, not settled facts. What is clear is that by the late Devonian, Jaekelopterus had disappeared. Two leading explanations stand out. The first centers on habitat loss and ecosystem change. Devonian waterways shifted constantly. Floodplains that once supported swarms of small fish and arthropods became patchy, fragmented, or disappeared altogether. Lakes shrank, rivers altered course, and estuaries periodically dried or changed salinity. For a predator specialized in rivers and transitional zones, these shifts meant its prey base grew unstable. Size and claws conferred little advantage when the food web beneath collapsed. The second ties its decline to competition. The Devonian is called the Age of Fishes, and not without reason. Armored placoderms and the first sharks began to diversify, entering the same ecosystems that Jaekelopterus once dominated. Though smaller on average, their advantages were decisive. Placoderms had crushing plates capable of breaking heavy armor, while sharks evolved streamlined bodies for swift pursuit across open channels. This meant jawed fish could invade the same niches, rapidly expanding and outcompeting larger arthropods for food. These twin pressures, habitat instability and competitive displacement, likely overlapped, and they unfolded not overnight but across millions of years. This was not a single asteroid strike. It was a long ecological shift through the Devonian that gradually tipped the balance against giant aquatic arthropods. Each generation saw rivers change shape, prey populations thin, and faster fish become more common. Eventually, the ecological space Jaekelopterus occupied was cut away from beneath it. The differences in hunting tactics help clarify this shift. Jaekelopterus excelled at ambush timing claw strikes in murky channels where sudden bursts of power worked best. But streamlined sharks could chase prey across open stretches, while placoderms could crush through shells that arthropod claws struggled to subdue. This created evolutionary displacement. Smaller, more adaptable predators flourished, while larger ones relying on force were pushed aside. Natural selection favored speed breeding rates and versatility over brute size and armor. Stress within populations may have made things worse. In times of shortage, many large arthropods turned cannibalistic, and Jaekelopterus likely did the same. Damage to eurypterid fossils suggests violent intraspecific encounters, claw punctures inflicted not on prey, but against rivals. If waterways diminished while food sources collapsed, internal pressures could have driven further decline, increasing competition between individuals already struggling in narrowed habitats. Even the question of size adds nuance. Based on isolated chelicerae, some studies argued that Jaekelopterus might have reached 2.3 to 2.6 meters long, making it the largest arthropod ever recorded. But not all researchers accept this scaling relationship. Kaiser and Klock suggested body estimates might be exaggerated, while Brady and colleagues defended the giant interpretation. Whether it grew to human-sized proportions or topped out closer to 2 meters, the debate underscores how much uncertainty still surrounds its natural history. What is not debated is that by roughly 370 million years ago, this line of giant arthropods was gone. Few natural predators of comparable size likely challenged Jaekelopterus in its prime. But as rivers changed and agile, jawed fishes spread, the balance shifted. The fall of the giant scorpion shows that dominance in one era does not guarantee survival in the next. Its extinction did not come with a single dramatic moment, but from a cumulative tilt in ecosystems that made speed, adaptability, and innovation more valuable than force alone. Jaekelopterus combined specialized claws and advanced vision to dominate freshwater edges, but environmental change and evolving competitors show that even giants are vulnerable. Its rise and fall underline a simple rule in nature: survival depends more on adaptability than on size alone.